Everyone, in this video lesson, we're going to be reviewing some vectors concepts actually, and talking about how to resolve vectors into components, how to add vectors, and we're kind of doing that in the context of some displacement and velocity in 2 dimensions problems. So let's get started. So it's a bit of a scenario to get you thinking. So normally, so you're driving north on some highway. Normally you just cross this bridge, but this bridge is now closed. So normally you would, from point here to point here, you would cross this bridge and you would have some one-dimensional displacement from here to here going north across the bridge. But in this case, because this bridge is closed, you have to travel east and then north across some other bridge and then west back to the point you would normally get at this detour. And what you've got is, instead of our single displacement, we've got a bunch of displacements: delta D1, delta D2, delta D3. They kind of add up and combine to result in the net total displacement that we would have had earlier just by going north. And so this 1D problem is kind of turned into a 2D problem. And our notion of speed and velocity changes a bit because, the displacement here is just a tiny displacement across the bridge. But, the distance here is not just the magnitude of this total displacement vector. It's the sum of all these individual displacement vectors. So for this trip, the average speed and average velocity are going to be a lot different than if we would just cross the bridge normally. So today we're going to look into some 2D problems and just do some simple problems like that. We don't just have to use the compass rose, northeast, southwest. We can analyze motion in a vertical plane, and the next 2 lessons we have are on projectile motion. So maybe somebody kicking a football flies through the air. In the absence of crosswind, it's going to kind of follow the path of a parabola, and maybe it's launched at some angle theta. So we're going to need tools to be able to analyze this motion, because at every step of the way, this projectile has a certain horizontal component of speed, and at the top might be kind of horizontal. Here we might have a little bit of vertical component of speed with a bit of horizontal component. On the way down, you have a horizontal component and it's going down. So we need to develop some tools, review some tools to help us analyze these situations in 2 dimensions when the motion is not in a straight line. Want to add, when we're looking at a vertical plane, like a projectile or a ski hill or anything, north, south, east, west don't apply. Those are what we would use in the horizontal plane, like in the bridge problem for staring kind of like top down, bird's eye view. Yeah, if we're kicking a football, I don't know if our friend was catching the football here, up in the air is not north, right? So we can't use northeast, west, south for vertical plane problems. In this case, if we wanted to state a direction, we might say so many degrees above the horizontal or below the horizontal, or straight up or straight down, or left or right, but not northeast, west, south. Let's just review a little convention for directions. So in real life, things just don't move north and east and west and south all the time. And there are some conventions. If the direction that's perfectly between north and east, making a 45-degree angle with both, we might just call that like northeast, right? And so if you see like northeast, it's halfway between north and east, but there's a lot of directions in between. And so our convention for labeling angles is the following. So just have a little visual here. So if we look at vector A here, we can say that the vector A, its direction is 41 degrees to the west of north. And this is the notation that we're going to use. Maybe you use something slightly different in your grade 11 course, but I think we all should, that notation should be kind of familiar to us. There's 2 more examples on here to help you get your mind around that. Vector B is 22 degrees north of east, and vector C is 15 degrees to the west of south. Maybe as a little exercise, can you just try this? Find my cursor here. Can you draw roughly where 30 degrees, maybe draw a vector D. That's 30 degrees east of south. If you want to pause the video and just draw that on your lesson sheet, or just visualize where it would be on this diagram, you can unpause when you're ready. 30 degrees east of south would be somewhere down here with an angle 30 degrees east of south. Now, while we're talking about vector D, there's actually a second way we could have labeled this one. If we make a 30-degree angle east of south, well, because east and south make a 90-degree angle, then vector D is also 60 degrees south of east. And those 2 directions are equivalent. One is not more right than the other, but some people do have a preference. Some people always like to do east and west of north and south first. Some people always like to have the smallest angle possible. So if you had your choice of these ones, they would say it's 30 degrees east to south because it's the closest to south. I personally don't care. So we're going to be using this notation, but as to whether you prefer to do east to south or south of east, it doesn't matter as long as it's the right direction. So the equations we have for displacement, final position minus initial position, and average velocity, displacement over time, they still apply to our motion in 2 dimensions. But here the displacement usually in our problems is going to involve more than one displacement. When that happens, we're going to refer to delta D as our total displacement. So back in this visual here, you can see that delta D we have labeled. Where's my cursor? Here, this is the total displacement. And this vector, delta D, comes from adding, in this case, our 3 different displacements. Each of those have their own, each leg of that journey has its own displacement. The total displacement is the sum of all those guys. And remember, when we add vectors, this would be something you guys covered in your grade 11 course. We add them tip to tail, right? So the vector delta D1 plus delta D2 plus delta D3, you draw delta D1. From the tip of delta D1, since we're adding delta D2, we draw delta D2. And because we're adding delta D3 to that, from the tip of delta D2, we add D3. And this gives us the vector sum. You draw a vector from where you started to where you ended. And when you're drawing a vector, a physical representation of a vector on a diagram, you should include the direction. And so here our final displacement is up. So kind of having set up all that, let's do an example problem together to kind of review these ideas. Or for some of you guys who haven't taken, it's been a long time since you've taken your physics course, maybe just kind of relearning it. So here we have a chickadee. So we're looking from the top down in the horizontal plane. You can see north is up on our page and east is right on our page. Flies from a post to a bush. And you can see that distance is 22 meters. And then from the bush to the bird feeder. So kind of 2 legs of this journey shown in this diagram. You'll see a lot of the questions we do you might be questioning, well, how do you get to figure 18? This is the first figure we've had. Well, I just pulled them from a resource and it just take too much time just to rename them all just because we'll just go with the flow here. So we're going to find total distance traveled, average speed, total displacement, and average velocity. And the one that will require us the most work and for us to use vectors is part C. And I'm actually going to review with you, show you 2 different ways we can do that. Let's talk about part A first. So part A is pretty straightforward. The total distance traveled, which we'll simplify with just delta D. is, we have two legs of this journey. There was a distance for the first leg from post to bush. I'll call it delta D1. It's 22 meters. And we have the distance for the second leg of the journey. Now, just as a little bit of notation, if I call that vector delta D1, so the first displacement vector, and this displacement vector, when I'm finding the total distance traveled, what I'm really finding is I'm finding the magnitude of these displacement vectors. That what we might refer to in math as the absolute value sign, we can also use to denote the magnitude of a vector. Now, personal preference, I would prefer, I understand that this is the true mathematical notation, but as I wrote earlier, I might just start my problem off saying, yeah, I know the total distance is just the distance of each of those two legs. So I might just use this notation for distance, just delta D1, delta D2 with no vector sign. So 22 plus 11, the total distance traveled is 33 meters. So really not a lot going on there. 22 meters from post to bush, 11 meters from bush to bird feeder. And if we know the distance, we can find average speed. Average speed is distance over time. 33 meters. In our time, we did have in seconds, 4.4. So this will spit out our average speed in meters per second. So let's quickly do that. And we get exactly 7.5 meters per second. And those are just scalars, no direction needed, distance, speed. So pretty straightforward. Nothing really crazy there. But let's now work on the total displacement. I'm going to show you, as I said, we're going to do two methods. So the first method is we're going to use components. So I'm just going to add a couple things to my diagram. So I'm going to call the vector from P to B delta D1, and I'm going to squeeze this in here too. We're going to call this second vector delta D2, and I'm going to label the resulting displacement vector just delta D. And we understand that this total displacement is going to be the initial displacement from post to bush, plus the second displacement from bush to fence. Now, like some people might label these as delta D, like PB, to illustrate that it's from post to bush, and then the second one is delta D subscript BF. Like, do whatever you feel comfortable doing. So the first method is we're going to use components. We know that the final displacement it looks like it's going to be maybe a bit longer than 22, and at an angle of, I don't know, like around 20 degrees north of east, just as an estimate. We're going to find out what that is exactly in two ways. And the first one is to use components. So I'm going to show you guys how we can break these vectors down into components. So I'm going to draw, first of all, and I'm not drawing these to scale, I'm going to draw our vector delta D1. And what we'd like to do is we'd like to break it down into a component to the east and into a component to the north. Now, initially, this angle makes a 33 degrees north of east. And of course, east to north make a right angle. So what we have is this right angle triangle. We can use our grade 10 math skills, right angle triangle trigonometry, to find what I'll label here is, I'll label this as delta D1x and delta D1y. That's how I prefer to label things. You are free to label things as you'd like. But using trigonometry, we have the hypotenuse being 22, and delta D1x is adjacent to the 33-degree angle. And so that means we would use cosine to find it. And using our skills from our grade 10 math course, we can write delta D1x is a hypotenuse, 22, times the cosine of 33 degrees. And because delta D1y is the opposite, we can see that's 22 times the sine of 33 degrees. And we can find those two components to the east and west. So let's do that right now. Do this one together. So 22 cosine 33, got about 18.5 meters, and 22 sine 33, pretty near 12 meters. So as our bird flew from the post to the bush, traveled 18.5 meters to the east and 12 meters to the north. And just to firm that up and just make sure we have, we understand what directions those are, I'm going to add the directions there. And I might pop some vector signs above there. And again, you use the notation and the structure that makes you feel comfortable. We all come, it's not like we're all took the same grade 11 course at our home schools and we're now all in the same home school in a grade 12 course. We're all coming from different spots. So notation, we're going to be a bit flexible. So what I'd like you guys to do is I'd like you guys to do the same thing with the second displacement vector. So we have our second guy, this 11-meter journey that's 28 degrees south of east. And I'd like you guys to find delta D2x and delta D2y. So if you want to pause the video and do that, I might squeeze them in here where I have some room. Again, if you don't want the spoiler, you can pause the video and try these on your own, but you're more than welcome just to follow along with me. So here, delta D2x, again, it's adjacent to the 28-degree angle. So we would have 11 times cosine 28, and we know that'll be east, and we'll have 11 sine 28. We know that direction will be south. So let's calculate those. 11 cos 28, 9.7, and that's meters, and we know that's to the east. And 11 sine 28, 5.2 meters, and we know that's going south. And everything's checking out here. If we think about the first leg of the journey, the bird travels 12 meters north, but the second leg only 5.2 meters south. So it makes sense from our diagram that that's going to let them be a little bit north. And that leads us to combining these together. So I'm going to move just to have some more room here, I'm going to move my hands and face up there. And again, the notation I use here, we're going to be a bit flexible with. So if you don't prefer this notation, you don't have to use it. But over both legs of the journey there, both displacements, what was the total displacement in the x direction? So we could show a step here, or many of you guys could just see it intuitively. But we have 18.5 meters east. Like you don't necessarily need to show this step if you see it. 18.5 meters east, and in the second leg we traveled 9.7 meters east, and so that's just going to give 18.5. Those are the same units, the same direction, so we can just add those together. 28.2 meters east, and in the y direction we had 12 meters north, and we're adding 5.2 meters south. So I'm going to show an extra step here. You don't need to show this step. Some of you guys could have went right to an answer, but 5.2 meters south is the equivalent of minus 5.2 meters north. And by subtracting those two, we get 6.8 meters north. So what we have is that the total displacement looks something like this. What we've just found out is that the bird traveled 28.2 meters east and 6.8 meters north. And what we're interested in is this final displacement vector. So to get that, we need the magnitude of this vector, how long it is, and we need the direction as well. So we're going to find, I'm just going to put a little theta there. If we can find those two things, we know the displacement. And we just use again, some math from our earlier math courses. To get the size of the displacement vector, now in this case, it's important to note that the size of the displacement vector here does not give the total distance traveled. The total distance traveled is the sum of all the magnitudes of these vectors. So delta d here is just the magnitude of our displacement vector. So we can get that using Pythagorean theorem. So we do the root of 6.8 squared plus 28.2 squared. We'll get that in a second. To get the angle, because we have the adjacent side, 28.2, and the hypotenuse, 6.8, we can use the tangent ratio. So tan is opposite over adjacent. So if we do opposite over adjacent and take inverse tan, so 6.8 divided by 28.2. So get that result and do inverse tan. It's going to give you the angle that we are north of east. If you do need a little bit of review of your like SOHCAHTOA, stuff like that, I would definitely maybe advise taking a pause, maybe going back over your grade 10 notes and just like brushing up a tad, watching a YouTube video, whatever you got to do. So for the final displacement, I got pretty close to, don't know why, to 29 to, sorry, I thought I made a mistake there, to 29 meters, pretty close to. And the angle, if I do 6.8 divided by 28.2 and inverse tan, I'm going to say 13.6 degrees. And so I can say that the total displacement, so we're done. The total displacement we can say is 29 meters, and the direction is 13.6 degrees north of east. Now, maybe for some of you might say, from the east direction, 13.6 degrees north. That means the same thing. But yeah, we've got it. So that was using components. The nice thing about components is that it relies on the just simple grade 10 SOHCAHTOA math, bit of Pythagorean theorem. And it's this process can be repeated with multiple vectors. So if I had 3 or 4 or 5 little mini displacements, my method would be the same. I'd break them all into east, west, and north, south component. I'd add all the components together, and I would recombine them at the end. It might take a while, but I could do it, and it's the same process, and I could even program a computer to do it pretty easily. But as you can see, it was like a bit of work. The second method is, and this is especially handy, if there's only 2 vectors, sometimes it might not be too bad just to draw the triangle and use trigonometry. So I'm going to show you guys that we should get the same answer by using trigonometry. So we're going to do the same problem a second way. So here we have our diagram set up, just the same diagram, and just note that remember that delta D1 was 33 degrees north of east. So if you can imagine a little Z pattern from your grade 9 course, this angle tucked in up here, this angle between delta D1 and an east-west line at point B is 33 degrees. And the second vector is still 28 degrees south of east. Because that allows us to get a couple things. So we know that, I'm just going to add this on here, that this side of this triangle, the length of delta D1 was 22 meters. So flip back, was 22 meters. And this side was 11 meters. And if we could figure out an angle in this triangle, we would have enough to completely solve this triangle and figure out angles and directions. And that's actually not too hard to do, because we know a straight line makes 180. So if we take 180 and subtract 33 and subtract again 28, it gives us 119 degrees. That is an awful looking one. I'm just going to actually erase that. It's like a backwards 7. Yeah, 119 degrees. And we can solve this problem using, well, at least initially, to find the size of the displacement vector, delta D, we're going to use the cosine law. So if you recall, the cosine law from your grade 10 course said that c squared. Almost looks like Pythagorean theorem, except you have to subtract off 2 times the 2 side lengths you have and times the cosine of the angle contained between those 2 sides. And so let's do that here. And depending on your comfort level, you might just be able to do this in one step. So to get c, you eventually would have to square root, and we're doing 22 squared plus 11 squared minus 2 times 22 times 11 times the cosine of 119. And we should get 29 if we've set things up correctly. If we did our work from the previous method correctly. I sure hope so. I don't really want to reshoot this video. 11 times cosine 119 and square root. Yeah, I got 28.98, so pretty much near on 29 meters. That's good. That's what we expected. And as far as the direction goes, what we're interested in finding is I'm going to call this angle alpha, because we know that this angle, the total angle, is 33 degrees. So if I knew this angle alpha, then if I know the total angle, I could find our angle theta, that is the direction north of east that I want. And so now that we have all 3 sides, we can use either the cosine law or the sine law. Now, just a real quick little bit of a mini math lesson. In this question, it's really obvious that the angle alpha in this triangle is acute. So the sine law would be totally fine. We're going to use the sine law. You could always use the cosine law because you have all 3 sides. It is possible to find any of the angles. If you're not sure if your angle is acute or obtuse, you should use the cosine law every time. But because I know for sure my angle is acute, I'm going to use the sine law. So for those of you who took grade 11 functions, that's the ambiguous case with the sine law. For those of you who've taken grade 10, you don't need to really worry about that. And I honestly don't think it'll come up at all in this course. But yeah, we're looking for sine alpha. So the sine law says that sine of angle alpha over the opposite side, 11, is going to be the same as the ratio of the sine of 119 divided by its opposite side, which we found was 29. And so to get angle alpha, we're going to get, we do 11, we're going to get sine alpha by itself and then do sine inverse. So we'll do 11 times the sine of 119, divide that by 29. That'll give us a decimal between 0 and 1, and then do sine inverse. So you can do that in 2 steps or 1, depending on your comfort level, times the sine of 119, divided by 29, second sine. All right, so I got about 19.4 degrees. And so that means angle theta would be, so remember the entire angle was 33. What's left over after you take away 19.4? It looks like 13.6. Which is great because that means that our displacement vector, the length of it is 29 meters, and the direction is from east 13.6 degrees north. It's the same thing we got earlier. Or again, if you like 13.6 degrees north of east, those mean the same thing. So we've done the problem 2 different ways. And I think this method illustrates the elegance and simplicity of just using trigonometry. Now, the downside of this method, the upside is that it's a lot less work. The downside is this method doesn't work well if you have more than 2 vectors, because then you have to solve this problem and then do a new triangle, do more trigonometry, sine law, cosine law. So that's the downside. So kind of in summary, if you have a 2D problem with just 2 vectors, trigonometry can often be easier and less work. But if you have multiple vectors, then probably using components is the way to go. But as you can see from this problem, they both gave us the same result. Let's finish this question off. What is the average velocity? So we know that average velocity is the displacement over time. and we have our displacement vector, is 29 meters. I'm going to include the units here in direction. It's 29 meters, and our direction was 13.6 degrees north of east. And the bird flew this in 4.4 seconds. And remember, when we divide a vector by a scalar, we do get a vector. So average velocity is a vector. And we're just doing 29 divided by 4.4. And we get about 6.6. 13.6 degrees north of east. So it's a little bit less than the size of that is a bit less than the average speed we got. So maybe think of it this way. The average speed we got earlier was 7.5 meters per second. So our chickadee, you can imagine our chickadee flying at an average speed of 7.5 meters per second from post to bush and then to bird feeder. If another bird started off at post and just flew straight for the feeder, if they flew at 6.6 meters per second in this direction straight to the feeder, they both arrive at the same time. That's kind of the connection between those two. So that's now when we're doing 2D problems, our average speed and our average velocity will often be different, with the average speed being higher than the average velocity. All right, so we've kind of reviewed some vector ideas, how to add vectors, using components, using trigonometry to solve a problem, and made some connections between average speed and average velocity in 2 dimensions. So next, we'll be able to tie what we've done with kinematics and what we've just kind of done with vectors and tie the two together to analyze a classic type of motion in 2 directions, and that's projectile motion. Now, for some of you, you might have done a lot with your grade 11 teacher on projectile motion, and others may have not done a lot, due to, depending on when you're watching this video, depending on whether your semester was cut short due to COVID-19 and you just didn't get to it. So we'll spend a bit of time on projectile motion. Hopefully it's review for a lot of you, but for some, you just might be kind of learning it for the first time, and that's okay. Hope you guys enjoyed that lesson. I definitely had fun making it. Hope you guys stay well. Please let me know if you need anything.